Okay. Hi, Assalamualaikum and good morning to everyone. Welcome to our webinar session for today. The topic for today will be 3D structural and mechanical properties of trabecular bone study by microcomputed tomography or MicroCT and finite element modeling. Today, our presenter will be Dr. Lim Fei Tieng, a senior application specialist from High-Tech Instruments, and also Associate Professor Insigne Dr. Ardiyansyah Syahrom, Director of MEDiTEC, iHumEn UTM. Before we start the presentation, let's hear a few opening remarks from Mr. Lai Ming Sun, the Division Sales Manager of High-Tech Instruments. Mr. Lai.
All right. Hi. Good morning. Thank you so much, Zul. First and foremost, on behalf of High-Tech Instruments, we'd like to thank Dr. Ardi and his whole team for organizing this and also having us to be part of it. And it's indeed a privilege for us to share with you all this technology on the MicroCT systems. And also, in fact, of course, during this pandemic, so there is no stopping us from sharing more advanced and technologies and developments to all our friends and who are out there. So thank you so much, and I hope you all will enjoy the whole seminar. And we look forward for more future collaborations with UTM and the team and Dr. Adi as well. All right. So without further ado, I'd like to hand over to my colleague, Dr. Lim. Over to you.
Hi, good morning, everyone. Thank you, Lai, and thank you everyone for joining our webinar this morning. And thank you, UTM and Dr. Adi's group for organizing all this and by utilizing their platform. This is the first time I had this Facebook Live, so it's quite interesting, a good experience. So today I would like to share about the principles and also what we can use of this X-ray MicroCT in vivo and ex vivo bone research. So I will start my talk by introducing the principles of this, how this X-ray MicroCT works, and then I will go into things that we need or factors that we need to be considered to obtain a good image quality. And after that, I will go straight into applications for in vivo and also ex vivo for bone research, like things that or factors that we need to consider before we start in vivo bone research. So let's move to a general introduction of what is an X-ray computed tomography, or we call it as a CT. So for tomography itself, it's the term came from this Greek word tomos, which means the slices, and it implies to object that when you get the cross-sectional images non-destructively. So it fits very well for our CT, what we call that X-ray CT here. And the computer itself, most of us will be thinking you'll be referring to a computer, but in this CT itself, it's not just means the computer itself, but it also means the synthesis of data, the generation of data from multiple images. And for X-ray, why we choose X-ray? Because the X-ray has a property that it can interact with the metal, with the material moderately, as into it will penetrate to a various depth without and being absorbed by the material itself before it's scattered or being absorbed by eventually without penetrate to or getting any data capture any data at the detector itself. So it's moderately, it can interact with the material. So partially of the X-ray beam can be absorbed by the material itself, and partially the X-ray beam will be detected on the beam, on the detector itself. So that's the beauty of X-ray and why it's being utilized to become a non-destructive kind of tools to generate CT images. And because of this criteria of X-ray itself is very suitable for imaging the interior of solid bodies. Of course, for X-ray, it has different energy level. For biological sample, mainly it will be in the range of 10 to 100 kV, whereas for material or metal kind of material like a carb or even for geology purpose, we have an X-ray which is with higher kV up to like 200 or 300 or even 400 kV of X-ray. So for different kind of material, which I'm going to talk more about the property, the attenuation of this X-ray. So here I've got this CT images. So I believe some of you might have seen similar images. It's a 7-year-old female patients with COVID. So you can see here is the axial CT images. And from here you can see this consolidation in this part here, the lung lobe here, with a higher density and with the blur boundary. So this is when the CT being captured at the peak when this 7-year-old having been diagnosed with COVID, with the and displaying the most severe symptoms of having hardness in breathing. So as it's recovering, when it comes to the 16 days of recovering, you can see the consolidation at the lower left lung lobe here has slowly disappeared, and it's actually correlate to the RT-PCR test with the nucleic acid SARS-CoV-2 test, which has been taken on 16 days, and it is tested negative. So we can see how does this CT images can be linked with other tests as well, and the confidence level and the importance, the information that provided here. So let's move on to the working principle of X-ray attenuation here. So attenuation means that the decrease of the intensity of the X-ray. So as you can see here, this is the decrease, the X-ray attenuation itself can be characterized or can be simplified into a Beer-Lambert law like this. So for this is actually representing only a homogeneous material, only one material with this distance or this thickness of homogeneous material. So you can derive this simple formula here. And from the formula here, you can see what is important will be the end intensity, the final X-ray intensity here. And the final X-ray intensity, it's depending a lot. First will be 3 factors. First will be the X-ray energy, the path length or the thickness of the material, and also the material attenuation coefficient of the material itself. So this we are talking about one attenuation coefficient from one material. So imagine when it comes with multiple materials, it will make the formula much more complicated. Okay, so this is a simple, not a simple formula. So this formula you can see here, when it comes with more than one material, so you can see the U here will have included the X and Y, which means it has 2 materials. It will make the whole attenuation coefficient changes by the number of materials itself, so it becomes more complicated. And this will give example like where you normally will encounter when you scan a live animal, whereby you want to differentiate between the bone, muscle, and fat. So this will be the energy level from low to high level. As you increase the energy level, you can see that the efficiency of differentiating between the bone, muscle, and the fat will be decreasing compared when you use a lower energy level. So when you are using a lower energy level, the efficiency for you to differentiate between all these three materials will be higher. But of course, with a lower energy level, the resolution might be affected. That's also another thing you need to think about before you start your experiment, whether your main objective is only targeting on the bone, or you would like to study other materials like the fat content and the muscle density, or the muscle, the measurement from the muscle itself. So that's one thing to be considered. And this one is just a simple animation. As you can see here, this one is the X-ray beam here. This is the material with different thickness. So as the incident beam travel through the object, when it's traveled through an object with a thicker and denser area here, you can see there are fewer X-ray that's surviving. Whereas the X-ray that penetrate through a less thinner area, or it penetrate through nothing, you can see that all the X-ray will be surviving. And from here, you will get this illumination here, or what we call it as a X-ray beam profile. So from here, it will be captured by the detector itself and will be delivered or will be sent subsequently for reconstruction to get the final slice image. So if you look at the component or the setup of X-ray MicroCT, it's pretty simple. It's just contain this X-ray source, this one, the sample holder or sample rotator itself, and also the detector. So this is a very simple setup, but of course it involves a lot of details within all these components here, especially the reconstruction algorithm itself, which is like the heart of the whole to get a good MicroCT image. So from here, I would like to share with you what are the criteria that is adjustable by user to further improve the image quality. So I've listed out, I think, 4 points. So one will be the X-ray spot size. I'm not sure whether the existing user, whether they realize that most of the system we can adjust. Normally we have 1 or 2 options to adjust whether we choose a smaller spot size or bigger spot size. So what is the effect of this X-ray spot size? You can see. So you can see this one with a smaller focus spot size. This one has a bigger focus spot size. So I can see here the geometric sharpness here, the edge sharpness here. You can see the effect of the size of the X-ray focus spot size. When you have a smaller focus spot size, you get a sharper edge compared to when you have a higher one. So most of the commercial MicroCT scanner will have micro focus, which is ranges between 5 to 50 micron. Some of the models allows you to adjust it freely, or some that already optimized with a couple of choices. So you might have the questions asking like, since the smallest focus spot size will give you the sharper image, then why do we still need to choose the one that with a bigger focus spot size? The reason being is that if you have a bigger spot size, yes, you will get unsharpness, you'll get geometric blur, but you will get a higher signal over noise ratio. So again, it depends to the quality of the image you can get. By using a smaller spot size, yes, you can get a sharp image, but your signal is very low. So that's where you can consider to increase the spot size so that you can get a higher signal. And okay, so I've talked about this one, the focus spot size. And another important factors to affect the quality, the image quality, will be this geometrical magnification, which I'm going to talk next. And this one I would like to highlight is that the focus spot size is limited by the power setting. it cannot be too small, because when it's become too small, it will generate a lot of heat that could melt the target itself. So that's why we have a limitation, and it normally ranges between 5 to 50 micron. It cannot be lower with the technology nowadays. So most of them will be ranges from about, the lowest is 5 micron. Okay, so move on. This one is an example. You can see here, this is with a smaller focus spot size. You can see the sharpness here compared to the one that with a higher or a bigger focus spot. And I would like to share with you this chart here. So as you increase the power, you will increase the spot size. So you will actually increasing the MTF. The MTF I will discuss later as well. And the MTF, we are calling it as an effective resolution. So even though the voxel size, which I'm going to talk also, the voxel size is the detector, the pixels of the detector remain the same. So it affects directly the resolution or the quality of the image. Okay. So next will be the scanner geometry, another factors, which implies on the geometrical magnification. So as you can see, this one will be the X-ray spot here, and this will be the detector. So based on the geometrical magnification, the smaller object, if you place closer to the spot, to the X-ray spot here, you will get a higher magnification with higher resolution. In return, you get a higher resolution, as you can see here. So if you place your sample closer to the X-ray source, you will get this geometrical magnification. So with this, you can see there is no magnification. It's a 1-to-1 ratio. Whereas for this sample, you basically can get about 3 to 4 times of magnification. But of course, the limitation is that of this field of view. So if you need to place it close to the X-ray source, meaning that the field of view or the sample size that you can insert or you can image will be smaller compared to if you place it here, whereby you can afford to insert a bigger sample size. Okay, so the next one I would like to share would be the angular steps. So if you see here, if you realize that the sample, after you position into the sample holder itself will rotate. This is what we call as angular steps. It will rotate to each rotation. It will capture one piece of data. So you can see for this example here, from what you see here, 225 projection or 180 degree, 450 and 900 projection. So for the quality of the image you capture here, you can see it's improving when we increase the projection number. So for this 225 projections over 180 degree means that every 0.8 degree of rotation, there will be one piece of data being captured. Whereas for this, it's about 0.4 degree. It will rotate 0.4 degree to capture one piece of data. Whereas for 900 projections means that it will rotate 0.2 degree to get one piece of data until it has rotated 180 degree. So from 0 to 180 degree, there will be a 900 projections that has been captured. So the smaller the angular steps, meaning that there are more data that being detected, being captured of the area inside the object. That's why you can see they are less artifact as you increase the number of projection or more data being captured. So it will increases the accuracy of the shape of the area inside the object itself. But the cons itself, the weaknesses of having captured more projection is that there are more times that will be consumed, like the scanning time will take longer. For example, if you take 225 and 400, basically there is a double of the scanning time itself. So for live animal, whereby the radiation exposure is a critical factor, then it will come to a issue so that you need to look for intermediate, look for a balance, whether you will require a fast scanning or you will require a good resolution with good data. So that's also one of the criteria you need to consider before you start the in vivo live animal scanning. Okay, so the fourth factor is the detector. For detector, it includes a lot of criteria as well, as you can see here. So what the commonly known one would be the pixel size. So the detector itself normally will say like how many hundreds of megapixels. So that's the common terms that we always heard for a detector. Other than that, we also need to consider the quantum efficiency, the geometric distortion, also the high dynamic range, and also the readout rate. All these factors need to be considered when you select a good detector. But for overall, the one that we user can change would be on the pixel itself. So what is a pixels? Pixels is if you experience to zoom in the image that you have captured, further zoom in to a stage that you can actually see the boxes like this. So each box of this is equivalent to one voxel size here. So we also call it as 3D pixels, which is equivalent to a voxels. And this pixelations here is adjustable when we select the matrix. So for most of the scanner, we are given a range of image metrics that we can select. Like for example, here we can select from range of 512 to up to 8K by 8K. Of course, the one that with lower image metrics, the data, or what you call that, the file size will be smaller compared to 8K by 8K. And again, the scanning time that will be taken for 512 definitely will be lower compared to scanning time to obtain this 8K by 8K of image metrics. So give you an example here. So this is a low mag. We capture by using a voxel size of 50 micron, and this is captured by using a voxel size of 60 micron. You can see here matrix here is 8K by 8K, and the matrix here is 512 times 512. And from this lower magnification image here, you wouldn't see much difference. So overall pictures looks okay. But the issue comes in when you further magnify it. So you can see here, the one that you capture with a voxel size of 50 and with the image matrix of 8K by 8K, you can still see the details very well, except that there is some noise at the background. So whereas the one that we capture, we set with a 60 micron here, we can start seeing the graininess, and it's very noisy, and the sharpness of the trabecular itself has like disappeared. Like you couldn't really differentiate well between the boundary or where is the bone itself or where is the background itself. And for of course, I understand that again, when it comes to in vivo scanning, we will come to a limitation of time. So one way to improve the signal over noise ratio is to increase the integration time here. So it will take a longer time, definitely, but at least it is still better than the one that we require a high resolution with a high sharpness, and also the file size. You can see the difference between 60 megabytes compared to 700 kilobytes per slice here. So you can see it's improved with the noise level reduced, and you can see a little bit of the pixelation here still. So this, the one that we capture with a good, a lower voxel size, will still give you the best image. And of course, the scanning time will be taking as high as 12 hours. So the overall workflow of X-ray MicroCT, so I have discussed about the X-ray source, the sample rotation, and the image that you can capture. And also, I've discussed about the importance of the angular steps. If we require a good quality of image, we should select the one that we're able to give you the highest angular steps, so that there are more data that being captured. It will be very critical if you would like to get good data, internal data, especially when you have an implant in the middle of the bone itself. So after this steps, all this data will be submitted for a reconstruction. Basically, there are a few types of algorithm, common algorithm for reconstruction. The common one will be called as filter back projection, and also iterative reconstruction. And last, you will get the 3D image. So for this reconstructed image, for the 3D image, it can come to two forms. One will be the 3D volume rendering, which is like this, or we can select the cross-sectional slices, like the first slide I have shown, lung lobe image. So you will see the slices instead of combine all of them into a 3D volume image. So combination of all these factors, it will come to effective resolution, the real final resolution, with combination of the X-ray spot size, the angular steps, and also the efficiency of the detectors. It will give you resolution, what we call it as a modulation transfer factor, MTF here. So this MTF, it's commonly used for but even though you buy a camera or you buy any sorts of MicroCT. So this MTF here is, you can define as a Fourier transform of the point spread function. And it shows how well the spatial frequency are being transferred to the final image. And to highlight is that spatial resolution here, MTF, is not equivalent to the spacing or to the size of the reconstructed voxels. So the reason why is that I would like to show you this image. Okay, the reason why this is a real silicon chip that has been used for MTF phantom to detect or to measure the final spatial resolution. So after being scanned by the MicroCT and being reconstructed and come up with the single slices, you will see an image like this. So from here, we can zoom in and we can start looking at the lines of frequency here, the different lines with different gaps. For example, here is 4 micron 4 micrometer of a line gap, and here is a 5 micrometer of a line gap here. So it's clearly that when you zoom in, you can see that the 4 micron is not resolved, whereas the 5 micron is resolved. So based on this value, we can say that the effective resolution of this system is it's considered as 5 micron. So basically, it's between 4 to 5 micron. That's why when you read the specification of the MicroCT, it will be written as less than 5 micron. So because it's in between of 4 to 5 micron. Okay. Okay. Come to the use of MicroCT for bone research. So the advantages of using this X-ray MicroCT for bone for any imaging is that first of all, it's a non-destructive method. You can use it for a wide range of specimens, from a very soft tissue like the lung, or even your heart, into mineralized tissue or harder tissue like teeth, bones, or even biomaterials like scaffold up to titanium or polymer can be imaged. And another advantage of this MicroCT is that it has a possibility to repeat the scanning because the sample is not being destroyed. So it's still in a whole intact piece. So you can scan it anytime after being treated by something. So after certain experiment, after certain treatment, you can scan it again to see the changes of your material. And another advantage is that you can also obtain a lot of both qualitative and also quantitative data. So for qualitative here, it means that it shows a good correlation between a histomorphometric data compared to a micro tomographic data. There is a lot of papers that are showing the correlation between the cross-section with the microtome section of a tooth, and then they compare to the MicroCT data to show the correlation. They see the precise, the exact correlation between the histostain section and histostain section compared to their MicroCT reconstructed image itself. And last, MicroCT has the advantage of providing a three-dimensional reconstruction image or data itself without requirement of sectioning the samples. Okay. However, the limitation is that there is a potential risk of to the operating staff and the research animal, which is we are talking about the X-ray radiation exposure. And when it comes to in vivo, if the radiation level is too high, it might cause some defect to the bone growth on the animal itself. So this is also something that we need to measure, we need to consider before we start the experiment. And last is that the sample size, it has certain limit based on different system. It will normally tells you what will be the maximum field of view FOV. So come to the application of in vivo. So the advantages of doing in vivo here, of course, the animal will remain alive. It allows a time lapse of monitoring of the effects. Like, let's say if you're looking at treatments of the drug or different diet or different hormones, whether it's on the tumor, the soft tissue, or the bone growth, or the regeneration, it will be a great method to use MicroCT on their in vivo animals. And it will be great for regenerative studies for limb regeneration or for the bone regeneration. And of course, by able to do these time-lapse studies, we can reduce the number of the animal needed for experiment. So this will be ethical issues here. And for the considerations here, when we start the in vivo experiment, first will be the animal handling. You need to make sure the animal are being comfortable throughout the scans. So what kind of tools is required to make the animal feel comfortable during the scanning, which I'm going to tell later. And the radiation exposure, I will share you 2 case studies to see how they study the effects of the radiation on the animal growth itself. And that will be the bone muscle fat separations. Okay. Here would be, you can see this is a rat being positioned on animal holder here. So from here, you will see that this is the anesthetic gas in and out. You can see there is a breath sensor, there is a gating scanning, and there is a temperature control. So the critical 4 things that we need to think of before we start the scanning, one will be that we should have breathing cycle monitoring system. We have the heartbeat monitoring. We should be able to control the temperature of the animal holder so that when throughout the whole scanning process, the temperature on the holder itself is constant to make sure that the animal can lie down there conveniently and comfortably during the whole scanning process. And last will be the use of drugs for this anesthetic process. So two commonly used anesthetic chemicals. One would be for one would be the ketamine. Ketamine can be administered by IP injection. So this is pretty safe and among the most commonly used anesthetic in wet medicine. And this ketamine is highly lipid soluble that is readily cross the blood-brain barrier. So it will make the animal lost conscious in a very short time, and it can the durability of this ketamine is quite good. It can keep the animal unconscious for quite a long time. Like it can go up to half an hour or 45 minutes or so. Depends on the dosage, of course. And another type, which is commonly used agent for inhalation anesthetic agent, would be what we call as isoflurane. So it's usually delivered at about 3.5% for animal size like a rat to induce anesthesia. And then it can be maintained by lowering the concentration to about 1.5% of isoflurane. So of course, this has to be optimized from animal to animal, and you have to make sure the body weight of the animal, you have to try to maintain or try to keep a range of the animal weight with this amount of anesthetic percentage. So the bigger animal, definitely you will need to increase the concentration or the amount of your anesthetic agent itself. So as you can see here, from here, there is another live observation camera that you can monitor the activity, or if there is any reaction or any sign of the animal gaining conscious. So that's the few things that can help to do the animal handling during the scanning process. So this is another monitoring setup for a rabbit. You can see this is the real monitoring heartbeat and also the breathing cycle. And also you can see it's also measuring the heartbeat, the pulse itself, and it's being administered with isoflurane gas itself constantly to keep the animal in unconscious throughout the whole scanning itself. So talking about how to lower the animal exposure to radiation. So there is some design of the MicroCT, they will prefer to use this narrow angle cone beam, because by using this narrow angle cone beam, it limits the region of interest being irradiated. So it minimizes the exposure of radiation to the animal itself. And of course, another, by using a wide angle cone beam here, you basically expose the whole area with radiation. And another advantages of using a narrow angle cone beam is that you can minimize the cone beam artifact, which is commonly appear at the edge of the detector itself. So that's some of these, depends to the design of the MicroCT also. Okay, so I have extracted 2 case studies looking at the radiation effect. For first case, it's looking at the rat itself. So it's being scanned 8 times. So weekly, so every week the animal will be scanned with a resolution of 50 micron on the left tibia, and this will be the setting for 70 kV, 1000 projection with 350 milliseconds. So it covers about 3.18 mm of the tibia, and the total scanning time is about 17.5 minutes. And this is the amount of the radiation exposure that will be absorbed by the animal itself. So for this setting itself, it will cost us 441 milli gray value. And the gray value here is the amount of energy radiation energy that being absorbed by the live animal itself. And you can define it as 1 joule of radiation energy per kilogram of the animal. So for this study, they have do let me show you. Yeah, the marrow bone cells. They have cultured the marrow bone cells to see the live and the dead cells after animal are being exposed to a radiation. So they claims that there is no significant difference on the absolute number of the live dead cells of their stem cell, the bone stem cell itself. So they come with conclusions that a radiation of 400 milligray has no significant effects on the bone structure, particularly in the rat, after 2 months of weekly high resolution scanning. So this could be a value that we can set for an animal if you are doing a similar kind of study. So make sure that your experiments are designed by limited the radiation exposure to the rat, to the animal here, to less or around 400 milligray. Okay, this is another case study as well. For this case, they are looking at both mice and rats. So both animals are being OVX, which means the ovary ectomized with the ovary removed surgically, and they are being scanned 6 times. So for mice here, because of the smaller body size, so you can see the radiation dose is higher compared to a rat here. And when it comes to the observation, you can see that there is no effect of radiation being observed in OVX and or sham intact rats, whereas there is some small effect being observed in mice. I believe it's because of the animal size that, as you can see here for mice, the effective radiation dose that being absorbed by the animal is about, I think, 30% higher compared to the rat. So it's about 700 milligray, which causes small effects on the trabecular bone of the mice itself, especially when the animal is immature and the bone is still growing. So you can see there is some defect or there is some stop grow rate on the bone itself. Okay, next, come to the bone muscle fat separation. So we, of course, if you're just focusing, your main target is on the bone itself, it's pretty easy. You just go to 70 kV and you can get a high resolution of the bone itself. But in some research, if you would like to look at the muscle or the fat, you would like to study on both fat and muscle itself. So you need to re-optimize, you need to find out carry that were able to give you a good differentiation between all these 3 materials. Like I can show you here. This is a short video. I can see a volume rendering. So from here, you can see the fat, the muscle, and the bone at different contrast level. Once we can get the different contrast level, we can utilize the software to do different segmentation here. If you are able to do segmentation by using the software, meaning that we can measure the density and also the volume of the fat, the muscle, and of course the bone itself. So from the bone, we can still further define the area, like separating the cortical and also the trabecular area of the bone. Okay. So this will be an example. A study for soft tissue analysis, sarcopenia, which is a syndrome or disease that characterized by progressive loss of the skeletal itself, skeletal mass and the strength. So from here, you can see the contrast of the muscle, which is different compared to the bone and the fat itself. So from here, we can do the segmentation and we can measure the bone volume and also, the muscle volume and also the muscle density. And the most famous bone research for in vivo would be the time-lapse observation to look at the fracture healing. So to ensure an accurate follow-up scanning, we can either scan the whole bone piece here, like example here, the whole tibia here. After we apply some fraction at the center here, we can do time-lapse monitoring over time to look at the healing. Or we can also utilize accessory like limb holder, which what you can see here. So the limb of the animal, for either for rats or mice, are being held nicely. So it is being clamped nicely so that you can define the area that you would like to scan, whether you would like to focus on the top, the epiphysis, or the metaphysis, or even the diaphysis area of the tibia. So every time when you click the animal, hold the animal with using the same holder, you get a precise follow-up, as you can see here. So this will be your starting scanning point. And from here to here, let's say it's about 5 mm. So every time you can stick back to the same setting so that you can get the accurate follow-up. So from here, you can see A, B, C. You can see that C, the trabecular, is reducing the amount of the trabecular. And by using MicroCT, in vivo or MicroCT, we can also study the cortical porosities. As you can see here, the healthy control and the diabetic control. So the green color here is labeling the porosity, the pores within the cortical layer itself. So you can see the diabetic has higher porosities compared to the healthy control. And we can also focus on the trabecular instead of the cortical itself. So you can see the porosities. And of course, all this will come with a detailed volumetric measurements. It's not just image itself. So these are the common parameters that you can extract from the report, like the total volume, bone surface, and all this. So from here, you will get an idea how much loss of the trabecular, or what is the thickness or even the porosities of the bone trabecular or the cortical bone itself. And in vivo bone research, you can use it to do this arthritis study, rheumatoid arthritis, which is a disease that caused by autoimmune, self-autoimmune, and it will cause a swelling and pain around the joints due to the corrosion of the bone and or damage of the bone. So from here, you can see this is the control. This is the RA patient. You can see there is a reduce of the spacing between the joints here, which you can get the measurement by using by submitting into the software and request the software to do the calculation to provide you the joint volume, thickness, and also the surface contact, the information in both image and also in measurement. Okay, and for some of the system, we can do a software that it allows you to do image registration. So what does it mean by image registration here is that you can do overlapping from your scan 1, scan 2 after 1 week, or scan 3 after 2 weeks. You can do overlapping, and from there you can do bone resorption measurement, like to identify the bone gain and the bone loss in the time-lapse observation. For example, this will be your scan 1, and when it comes to a second scan, you can do a total overlapping by using a special script from the software itself. So from here, you can see that the green part is the bone gain, then the red color is the bone lost. So by having this kind of bone resorption measurement, it can give you a better idea whether compared to the first scan, whether there is a increase in terms of a new bone, or there is a loss of the bone material. So this is another example that you can see here. This is the baseline that you can see that you capture in week 1. After 1 week, you can see there is a green color, which is the opposition, the new bone, and the pink color, which is the bone resorption. So by the end of 12 weeks, you can see that the gap here are being filled by the new bone, the bone opposition here. So from this study, we can get the result of reorganization of the trabecular bone, the bone regeneration, and we can also see there is a regeneration, a grow back of the trabecular bone that's going to fill up the gap here. And for in vivo study, we can do osseointegration. Of course, for osseointegration, we can do it in both in vivo or in vitro method. It doesn't have to be in vivo if you are willing to, if you're ready to sacrifice the animal. So for osseointegration studies, the main focus is on the contact surface around the implant here. For example, this one is a 2D cross-section. This is a bone. This will be an implant. And this will be the 3D reconstructed model here. So from the software itself, it can also provide you data like this, a contact surface. So this is a graph that gives you the idea how many % of the surface are being contacted or attaching with the implant itself. And of course, not to forget, we can also get volume rendering itself. So with this kind of data, we can get information from a 2D slices, from a 3D reconstructed model with different color labeling to indicate the contact surface. We can also get a volumetric kind of measurement in numbers in a graph form, and we can also make it into animation. Okay, so this one, I think Dr. Adi will talk about it more on the final element analysis. So for in vivo bone research, we can also do biomechanical properties by utilizing a final element analysis here. For example, this bone here, they are doing distribution of bone missile stresses. So this is the setting that, or the standard calibration or standard criteria that being given to a final element analysis. So it says here, you see the estimated failure load was computed based on where the fractures are assumed to occur when 2% of the bone tissue is strained beyond a 7,000 microstrain. So by submitting into a final element analysis, it can predict the fracture, the risk of the fracture itself. As you can see here, the red color area is having a higher risk, higher fracture risk compared to green and the blue color. So interesting things that you can see from here is that the trabecular, even though in a high porosity sample, it's actually having low fracture risk compared to the cortical, which means that the cortical will actually collapse before it comes to the trabecular area here. So you can see both distal and proximal area, and you can see the color coded here to show you the chances of the bone being at that particular area of being a fracture when there is an increase of a stress. So other than bone, a final element can also use on material sample. This is a very interesting sample that I would like to share. So this one is a stent. It's a tiny tube that the surgeon will insert into the blocked coronary arteries to improve. So you see it's expanding the stent to improve the blood flow itself. So you can see the blood flow will normally come from this direction. So this will be inserted into the final element studies. Will be provided this kind of information from this direction to this direction. So, and this one is the prediction of the final element. It shows that after being projected with this flow rate, certain flow rate, and being expanded after crimping, the stresses are localized, you see, at the U band region here, which means that it will experiences the lowest state of expansion. Or in other words, it will collapse the fastest compared to the other area. So that's the beauty of using a finite element analysis to do the fracture risk prediction or this deployment of material. Okay. So comes to the ex vivo. Ex vivo can be doing everything that in vivo is doing, except that the animal cannot be alive. So that's the limitation. So in other words, ex vivo, it has unlimited application. You can use it on bone, tumor, soft tissue. You can use it on plants, implants, grafts, biomaterials, materials, polymers, on all sorts of sample. And the advantages of ex vivo application is that it allows high spatial resolution because it allows longer scanning time and without a limitation, without worries on the radiation dose that being exposed to the material. So we can submit it for scanning for the best resolution, the best image possible without worrying about the radiation being exposed. So, and it will be ideal for microstructure imaging. Apart from trabecular bone, we can do vascular casting, and we can do vascular casting in the brain, in the cardiovascular, in the kidney, and other organs. So this is an example by looking at the details or the microarchitecture of the trabecular itself. So here is the reconstructed femur. And of course, we can make it into animation. You can see the fine structure of trabecular itself. And because of its high spatial resolution, you can see that we can further zoom in, and yet we can get, we can see the 1 micron width of a gap on the cortical bone itself. And we can utilize it to do, to expose high resolution networks or vessels. For example, here is the Haversian canals, which is the network that you can find in the bone itself. And normally it will contain blood vessels. So you can see the solid here is the cortical, and the green, the one that color coded with green and yellow would be the canals itself, which also representing the network of the blood vessels. So this again, you can see the solid part is the higher density of the bone, cortical. When you inverse, using the software, when you inverse, the solid become transparent, and the transparent or the pores here become solid. You can see much more information. For example, you can see the tube here is representing the Haversian canals, and also the small dots here all around the cortical bone here is the osteocytes. So these are some things that we can utilize the high resolution and the software of the MicroCT to provide us more information, except than just the conventional data like the density and also the TBTV, the total bone volume and the porosity. This is something that we can play around to reveal more information. Okay, so we can characterize the bone strength. Of course, this one is the bone that's being extracted. So it's an ex vivo sample, and we can do a 1:1 3D reconstruct models, and we can do thickness mapping of it, and we can do cross section. Of course, it's a software type of cross section without a physical construction to expose to the area. So you can see here, this area is thicker compared to the green area. Hold on, it hangs. Okay, so of course, similar to in vivo, we can do porosities and thickness measurement. So you can see the red color here, red color label here is representing the pores within the cortical layer. And here we are doing a thickness mapping of the whole bone from the cortical and also the trabecular itself. And we talk a lot about rats and mice and rabbits. And not to forget that we can also do interesting bone research by using a lower vertebrate animal, for example, like amphibian and even for fish. So for trend nowadays, amphibians and also fish are becoming a very famous, very good model, popular study models for their limb regeneration. And for lower grade vertebrate, it has less issue, especially on their radiation exposure. So it will be a good model to use for bone research as well. And we can, and because of the small size, we can do it by even using an ex vivo MicroCT. And we can view, we can scan the animal when they're alive. So this is an example of doing Kiko. And I have also found an example by scanning a zebrafish. And last will be this vascular casting imaging, which allows you to get a clear vascular of a mouse brain and also a mouse kidney. But of course, this has to be incorporated with effective or a good contrast agent before you submit for scanning. So that's all for today that I would like to share. I think for Q&A section, we will open after presentation from Dr. Adi. So I would like to welcome Dr. Adi to share his studies on finite element. Thank you.
Thank you very much, Dr. Lim. And I will continue the session. Yeah, I will continue the session with the modeling in the trabecular bones mechanics and the nutrient transport in trabecular bones. Okay. Thank you very much to HiTech to combine the webinar series related with MicroCT. I will also to thanks to everybody to join this webinar. Okay, today, please, I will try to introduce the MEDiTEC. Yeah. MEDiTEC is this is the structure of the MEDiTEC. Yeah, in MEDiTEC there is on the top there is Institute Human Centered Engineering. Yeah, this is a combination of the 4 center. Yeah, there are 4 center. The first is IGN UTM Cardio Center that is focused with the cardio. And the MagicX. MagicX is Media and Game Innovation Center of Excellence, and Sport Innovation and Technology Center (SITC), and MEDiTEC itself, Medical Device and Technology Center. Okay, this is the vision and mission of the MEDiTEC. to be global research in center in medical device. The mission is conduct research, development, commercialization of innovative and competitive medical device technology. Okay, if you're looking here, actually the result from MicroCT scan, this is osteochondral. Yeah, the yellow one is actually cancellous bone. The pink one is subchondral bones, and the blue one is a cartilage. Yeah. Okay, this is the strategic UTM. UTM MEDiTEC, yeah, medical device technology within 2030. Okay, we have the three focus area. The first is the implant technology. Another one is bioinstrumentation and bioinformatics. Yeah, but we have do all on in medical device, but we focus on these three. Okay. Then this one is MEDiTEC teams. Yeah, MEDiTEC teams. This the director is me, Ardiyansyah Syahrom, and the deputy director Dr. Muhammad Hanif bin Ramli, and senior research fellow is Professor Dr. Muhammad Hasbullah bin Haji Idris, and associate professor engineer Dr. Rubita Sulaiman, and Dr. Amir Putra Ahmad Saad, Dr. Ami Saleh, and we have also associate research fellow. Yeah, associate research fellow is Dr. Nur Jihada Izzah binti Ismail, and Dr. Asnida binti Abdul Wahab, Dr. Nurhana Yusuf, and we have supporting staff is research officer Zulfatli bin Zakaria, technologist Zulfatli Zakaria, and assistant engineer is Norazwan Abdul Rahman. Okay, and we have visiting research fellow from Laval University, associate professor Dr. Hendra Hermawan. Okay, from Canada. Okay, we have one professor, two associate professor, 6 near lecturer, 1 research officer, and technical staff. Okay, we go to the main presentation today is mechanic and nutrient transport prediction of the trabecular bone. Okay, this one is focused on only on the trabecular bone. Okay, in at the microscopic level, all the bone is composed to type of osseous tissue. Is the first is cortical or the compact bones. Second is cancellous bone or trabecular bones. Today we focus on the cancellous bone. Yeah, cancellous bone is type of the osseous tissue with a low density and the strength but very high surface area that fill the inner cavity of the long bones. And external layer cancellous bone contain the red bone marrow, where the production of the blood cellular components known as hematopoiesis takes place. Cancellous bone also where the most of the artery and the vein of the bones organs are found. And the cancellous bone, there is another function is as a load bearing. Yeah, they can support up to 70% of the load. So if you give the load, 75% take by cancellous bone as absorber. Okay, this is type of the bones. Yeah, classification of human bone according the type and shape. The flat bone, let's say, sutural bones, short bones, irregular bones, yeah, marmoid bones, and the long bones. Yeah, in the every joint there is a we call trabecular bones. Yeah, in every joint of these bone there is a cortical bone, trabecular bone. Okay, this is an example. This one bone. Okay, we cut and we take the cylinder, then we can see the porosity of the cancellous bone. Okay, then if you scan, it's become like this. Yeah, there is a porous structure. Okay, and this one also after reconstruction of the trabecular bone. Okay, this one you can use on the MicroCT scan. Okay, you can use the CT scan because that is with a higher resolution. Yeah. Okay, there is a question. What do you need for the bone graft development? Yeah, there is two units. Okay, the first is the bone mechanics. Another one is the nutrient transport or the fluid flow in the cancellous bone. Okay, and we need to study first related with trabecular bones. Then after that, we able to develop, construct the bone graft. Yeah, that is make your bone graft is become better. Okay, let's say in bone mechanics, you're looking on the mechanics of the bone, and nutrient transport, you're looking at the fluid flow in the bone. Yeah, in bone there is a fluid flow also. Yeah? Later I will detail. Okay, we go to first in the microarchitecture. Okay, about microarchitecture of the cancellous bone. Structure and microarchitecture are determinants aspect of the bone strength, an essential element for the assessment bone mechanical properties. Yeah, and this is really important. Microarchitecture that can be affect anything. The change of the mechanical properties, a change of the nutrient transport. Yeah, then in the end, they change the nutrient supply to the bone. Then we can identify the bone is become healthy or not. Okay, the microarchitecture factor is fractal dimension. It's used to estimate the bone strength. Yeah, with the microarchitecture, we can determine the values of the bone strength. Yeah, with any joint, any anatomy site, that is different properties. That is depend on the microarchitecture itself. The microarchitecture of the bone tissue refer mainly to the morphology of trabecular bone compartment. Its structure feature include the volume, shape, number, thickness, connectivity of trabecular present, plus marrow in modality cavity. Yeah, that is the microarchitecture of the cancellous bone. Okay, we can check here. Yeah, from the MicroCT, we can analyze like that Lim mentioned before. Yeah, we can study let's say the normal osteoporotic cancellous bone. Yeah, we can check the porosity. Let's say how many percent, or the surface area of the cancellous bone, how many percent. Then after that, we can identify the bone is healthy or not. Okay, this is one example. Microarchitecture of cancellous bone. This is an example we analyze of trabecular separation. This one we analyze of trabecular thickness. Yeah, actually we can the slicing. Okay, after the scan, maybe you can have the 1,000 of slice of cancellous bone. Yeah, the diameter, let's say 8 millimeters or 10 millimeters, and the length is 12 millimeters. This is you can construct around 1,000, more than 1,000 slice. Yeah, then after that you can study the morphology of the cancellous bone. Yeah. Then after that, you can identify the properties of the cancellous bone. Yeah. In terms of the mechanic and the fluid mechanic in the cancellous bone. Okay. This is another example. Let's say after scan, you can reconstruct. Yeah. You have slicing in here. We take 800 slice of the features. Let's say data obtained from MicroCT. Yeah, with the show raw scan image file and demonstrate B is demonstrate image file are stacked. Yeah, in sequence accordingly to scan sample orientation. Yeah, after that you can construct is become like this. With that one, you can manipulate. Yeah, you can manipulate or you can analyze. Okay, this is example of the morphology of the trabecular bone. Yeah, this is the common volume fraction, trabecular thickness, trabecular separation, bone surface, bone volume fraction. Yeah, the degree anisotropy, connectivity degree, SMI, and the porosity. Yeah. Then after that, you can analyze what effect of the micro architecture with the mechanical properties or the fluid flow in the cancellous bone. Yeah. I go to biomechanical properties of the cancellous bone. Okay, biomechanical properties is this is the biomechanical properties of idealized unit cell cancellous structure. Okay, this is one example. After we construct of the trabecular bone, yeah, from the MicroCT, yeah, and after that, in study on the trabecular bone, we can study by unit cell. Okay, in trabecular bone is a very unique unit cell. Okay, this is 8 sample of the unit cell. You can take from here one by one. Then after that, you analyze. Yeah, that is depend. They say if you have a good workstation, then you can have the large sample, right? But if your, let's say, in the workstation is not too good, then you can analyze to predict mechanical properties of the trabecular bone with biunit cell. Okay. After that, we can develop the unit cell of idealized trabecular bone. Yeah. Then after that, you can compare the properties of both unit cell. Okay. Which one is better? Is to represent of the cancellous bone. But here we focus, let's say, by unit cell, yeah, then able to predict the walls of the structure. Yeah, this is one example. Yeah, we use the periodic bone theory condition to analyze unit cell and predict the bulk of cancellous bone. Okay, this is one example. Yeah. From the analysis. Then after that, we normalize. This is between the volume fraction. Yeah. Then how the relationship between volume fraction to the strength, the strength of the unit cell of cancellous bone and other structure. Okay. This one we can do the test. Yeah, in the cancellous bone. Yeah, we can do experimentals. Yeah, before we compress here. This is after the compress. After that, we can check the fail of the cancellous bone. Yeah, we can check here the fail of the cancellous bone. Then actually, if you have a workstation, you can compare. Yeah, you can compare the model of the experiment with the simulation. Yeah, that is actually you can predict, you can simulate the exactly, and you compare with the experiment one. Yeah, even though the fracture line with the same model, you can get exactly the same with the experimental. Yeah. Okay, with cancellous bone, with MicroCT, yeah, we can check actually during the testing. Yeah, we have 3 types of the fracture. Okay, the first is we call the oblique fracture. Another one is global fracture, and another one is a localized fracture. Okay, this one percentage, yeah, of the fracture type. Okay, let's say in the localized fracture, actually, if you check on the model, check in the specimen, the model like the specimen will intact. Yeah, will perfect. There is look like there is no fracture. However, when we check with the MicroCT, actually there is a fracture. yeah, by scanning. Then after the test, you scan, then you can check here where the location of the failure. That is we call the localized fracture. If the global and the oblique fracture, that is obvious, mean you can see by clearly, you can see the clearly of the fracture line. Okay, in fact, the sample is become 2. Okay, but in the localized, you need to another tools, yeah, to check. That is why the failure of the trabecular bone. Actually, the trabecular is failed, but look is okay. But inside, then there is a fracture, a lot of fracture. Yeah, there is a fracture here, there is a fracture. Then you can check also with the image analyzer. Yeah, you focus, then you can know there is a fracture. Yeah, yeah, there is a fracture. There is a fracture under trabecular bone structure. Yeah, that's why the strength of the cancellous bone is become failed. Okay, this is like you study morphology, yeah, with the with all the type of the fracture, yeah. Then the effect, let's say porosity with the scattered fracture, oblique fracture, or perpendicular fracture. Then you can check. There is effect, let's say, on the porosity, density, edge density, on the volume fraction. You can check which one the effect, more effect to identify type of the fracture in the cancellous bone. Okay, this one the example. Yeah, after you scan, after that you study and everything, you have analyze all the microarchitecture. Let's say the density, how much the density, and the edge density, the porosity, trabecular separation, trabecular thickness, and volume fraction. Yeah. Then after that, you can check also on the ultimate strength. Yeah, initial yield strength, the yield strain, the elastic modulus, let's say. Then after that, you can study, yeah, the effect of the mechanical properties due to microarchitecture of cancellous bone. Okay, let's say like this. Okay, we can check, yeah, how modulus effect with the volume fraction, how the from the analyze, the volume fraction actually affect more in terms of mechanical properties of trabecular bone. Yeah, let's say we can check here, we can see here the modulus correlation with the volume fraction, ultimate strength with the volume fraction. Yeah, initial yield strain with the volume fraction, and the yield stress with the volume fraction. Yeah, but before this, we check which parameter microarchitecture that is affect the properties of the cancellous bone. Okay, and we know the mechanical properties. Yeah, mechanical properties. There is a static properties. Let's say the first I present, then second is the fatigue properties of the cancellous bone. This one I looking on the uniaxial and multi-axial fatigue life prediction. Okay. Okay. This one for simulation. Yeah. This is the model how we can simulate. Actually, this one is the percentage body weight of the gate motion. Yeah. This is the gate motion in the Z direction. That one is the X direction, and the green one the Y direction of the gate cycle. Then you turn, it's become the equation. After that, you can simulate. Yeah, you can simulate of the simulation. Okay, this is the model. That is what we construct from the cancellous bone. Then after that, we check the fatigue life of the cancellous bone. Okay, we do here actually experiment and the simulation. Yeah, experiment and simulation. There is a, we compared here also with the uniaxial and multi-axial, and also we compared with the gate loading also. Yeah, like I mentioned before, there is a gate loading properties. Yeah, then you can submit in term of the simulation. Okay, this one is the figure reducing of the strain percentage with the cycle to failure. Okay, and this is the black one experiment, and the FE, yeah, the red one, and the FE gate, yeah, the gate loading with the blue one. Okay, you can compare here. Actually, if you are looking here, the gate loading actually make cancellers is more faster to failure. Yeah, compared let's say with the uniaxial. Yeah, uniaxial. That is, you can check here the comparison, and also we can check comparison uniaxial and multi-axial loading relationship of the applied stress to effective strain correspondence to vertical direction change strain. Yeah, the high fatigue region HCF, and the start from the end more than 100, whereas the low cycle fatigue region is LCF is range 0 till 100. Okay, like in the beginning, let's say 100, below than 100, we call the low cycle region, fatigue region, and the high fatigue region. You can compare actually multi-axial and uniaxial of the fatigue life in the cancellous bone. Okay, this one is the advantage if you have the model. Yeah, after the testing, after you prepare the sample, then you can scan, then you can manipulate. Yeah, you can manipulate anything. Yeah, you can analysis. You can compare with the experimentals. If you compare, if you did only experimental, then you need to load a sample. That actually more expensive. Yeah, better if you have this kind of the technology that is make it easy to us to reconstruct all the model. Then you can manipulate testing, type of testing. Yeah, then is make more cheaper in terms of the analysis. Okay, this one the comparison, yeah? Comparison the uniaxial loading and multi-axial loading. Yeah, then you can check here in the 10 cycle. Yeah, number to failure is high. Yeah, then after that is become high percentage of the loading with the they will you can check here. Yeah, there is a red one that is caused near to failure, yeah, of the cancellous bone. So multi-axial is more faster failure in the trabecular bone structure. Yeah. Okay, this one another comparison. Yeah, another comparison is multi-axial loading and the uniaxial loading. If you see here, yeah, in the multi-axial loading is really fast degrade in terms of the strength. Yeah, that's why the failure is very fast compared with the uniaxial. Multi-axial means you combine the load, your torsional with the compression. Yeah, this one you can check also the what the effect. Yeah, we check, we can check also the morphology that is effect to the fatigue of the fatigue life of the trabecular bone. Yeah, if you check here, the most effect, the first is the volume fraction. Another one is trabecular bone thickness and connectivity degree, yeah, and the SMI. This one is the more effect to the failure of fatigue failure in the trabecular bone. With the multi-axial loading is volume fraction, trabecular thickness, and the SMI. Okay, means if you're looking here, there is three microarchitecture factor we need to concentrate, which is the volume fraction, trabecular thickness, and SMI. Yeah. Here also we can looking on the correlation. Yeah, which one is more correlated in terms of the numbers of the failure, cycle to failure, with the volume fraction and the SMI. Yeah, here we can know uniaxial is more has a correlation with the volume fraction. Okay, the same like SMI. Yeah, uniaxial with the high correlation compared with the multi-axial. Now we go to fatigue properties of the cancellous bone. Yeah, we can check here the effect torsional loading to fatigue life prediction. Yeah, if you check here, we try to simulate, let's say, the compression 25%, and we give 25% of the compression, 25% of the torsion, and another one is the 50% to 50%. Yeah, after that we combine, let's say, then after that you can compare. Yeah, which one? Okay, you can check here in the graph. Yeah, if you check in the graph, here the figure of the modulus reduction profile, the A at the various stress level, yeah, and the B is modulus reduction of the each loading component of the sample under combined compression torsion is compared with the 50 compression, 25 compression, and 50 compression and 50 compression. Okay, then you can compare here. Okay, 25, the first model 25, and the 50, yeah, 25 compression, 50 compression, torsion is maintained the 50%. Then we can check here. There is change the properties. Yeah, there is change the properties. Okay, numbers of cycle is really fast in the point B. Okay, and the 25 compression with the 50 compression, 25 torsion, then the cycle of the failure is quite high, yeah, compared with the first. That is 50% of the torsion. Okay, if the model we can compress the 25% compression with the 50% compression, there is a difference. But in here we can know that is torsion effect is higher, yeah, compared with the others. So meaning the cancellous bone is not good have torsional load, yeah, a torsional load. So that's why in the sportman they say if they do something extreme, then the crack in the bone is more possible compared with the movement is a normal one. Yeah, you can check also here. Here is a sample 1 is compression, sample 1 is torsion only, and another sample 2 the compression, and sample 2 is torsion only. Then the properties will be different. Yeah. Then how you can check the effect of the torsional. Okay. Here the type of the fracture. Yeah. You can check also in the SEM. Okay. Surface fracture on the sample under pure compression. 50% of compression after 1 million cycle, and the micro crack on the trabecular bone strut, and the same sample, higher magnification. Yeah, here the surface fracture. Then after that we check on the strut. Okay, then you can see the micro crack in the trabecular structure. That is initiate of the filer of the trabecular bone. Yeah. So here the SEM monograph of the sample, yeah, compression. Okay, here you can check the filer. Okay, there is 3 direction of load. Yeah, micro crack on the strut, surface fracture. Okay, and the fracture and the C, and the fracture in the fiddle strut. Okay, there is a fracture in the fiddle strut, and the buckling effect. So with all the technology, yeah, you can check type of the failure and everything. Then you know the detail why the structure is failed. Yeah, let's say with the MicroCT is more easy. Okay, now I move to nutrient transport in cancellous bone. Okay, okay, actually this one the rig that we developed, yeah, the rig that we developed, here we use a SBF, yeah, that is a water bath. The SBF, we control the temperature 37 degrees C. Okay, this is the sample holder, this one, yeah, the blue one, this is sample holder. Then we put the sample inside. Then after that we give the flow rate. After that you can check the resistance of the sample. That is mostly we looking on the permeability. Okay, in here we study on the multiple region. Yeah, you can compare. Here is neck, trabecular bone. Here is trochanter. Yeah. Okay, this is trochanter, and this one a mediolateral femoral condyle. Okay, after that we take the sample, then we compare. Okay, here we compare also is the natural cancellous bone with the synthetic cancellous bone. Okay, then you can study here. You can see here. Let's say this is the permeability of the femoral condyle. Here the trochanter, and here is the neck of femur. Yeah, that is neck of femur is a high permeability, mean the porosity, volume fraction is become low. Yeah, with the high surface area in the cancellous bone. Okay. Okay, this one the relationship, the permeability with the porosity. Yeah, we can check also how the relationship in terms of permeability and the porosity, and also we can check also what is the importance. Another one in the bone surface area. Yeah, with the permeability. Okay, with the MicroCT we can identify with the bone surface area. In the porosity, without a MicroCT we can analyze. Yeah, we can calculate using the another method, conventional method. Yeah, but in the bone surface area we can't. We need to scan the sample, construct and analysis. How much we can count the bone surface area. That is the will effect on the permeability of the cancellous bone. Permeability is the main factor at the consideration for nutrient transport. Yeah, if you has the higher permeability, mean the flow is fast. That is no time for your bone to dissolve of the nutrient. Yeah, to absorb of the nutrient. That's why with the osteoporotic bone, yeah, the permeability is quite high compared with the normal bone. Yeah, that means the absorbance of the bone is less compared with the high surface area or the porosity. Okay, after the test in the experimental, also you can simulate. Yeah, you can simulate. Here we simulate a lot. Yeah, there is a natural cancellous bone with the synthetic cancellous bone. Okay, if you're looking here, we use here the fully CFD, computational fluid dynamic in cancellous bone. Then after that, you can study how the flow pattern in cancellous bone. Then which one you can develop or you can construct the bone graft or synthetic cancellous bone that is similar with the cancellous bone. Yeah, you can check also in the mechanic like previously, and you can check in terms of the fluid mechanics. Okay, and another method is the first you can use the fully CFD. Then actually it's more advanced. You can use the fluid structure interaction on the cancellous bone. Okay, you can apply here. We try to use the gate loading. The gate loading, okay, of the sample, like in the left side here. Okay, you can check. You can apply the load gate loading to your model. Then actually you can more easily compare. Yeah, you can get straightforward. You can get the fluid mechanic and you get the mechanic. Okay, here the fluid structure interaction. This is the fluid. Yeah, this is the fluid. This is the velocity. Yeah, this is the velocity. The numbering is the velocity. Okay, here the compression during the compression. Here during after unloading. Yeah. So this one is the during the compress. Okay, the pore size underneath will increase in terms of the pressure. If the unload and the top region is more higher, the pressure is more higher compared with the underneath. Okay, actually there is a function. Yeah, there is a function. Actually, the marrow during the loading actually is a function also a support. But if you have there is excessive load, the movement of the marrow is very fast. That is able to break the strut of the cancellous bone. Yeah, that is actually need to balance. There is the maximum level of the velocity in the marrow. Actually, is not the break of the strut in the cancellous bone. Okay, here, yeah, we try to compare. Let's say fully solid mechanics. Yeah, simulation with the fully solid mechanic. You compare with the FSI. Actually, the properties totally different. Yeah, in terms of the mechanics. Here we're looking only on the mechanics. Yeah, we're looking on the mechanics. Here totally different. If you are check here with the same everything, yeah, with the same everything. If you check here the contour plot, yeah, the red color is a lot here because in here there is no function of the support in the marrow. Yeah, that is the importance of the marrow. If you look on the B, the fluid structure interaction, the red color only in the specific point, but in the cancellous bone, the pore size here, it is not take high stress because there is absorber. Yeah, there is support from the marrow. That's why the stress here is not too high compared with the purely solid mechanic. Then this is the most important. Yeah. Then, if possible, if you want to predict the properties of the trabecular bones, if you have the model, then the better use the FSI approach. Yeah. Then the result is more comparable compared with the experiment. Okay. Here you can check the difference between the fully compression solid mechanics and the FSI. Thank you very much. This is our teams with all the students. Yeah, this is the youngest one. Yeah, MEDiTEC members. Okay, 5 years old. Okay, thank you very much to the participant. I will end. Assalamualaikum warahmatullahi wabarakatuh and good morning. I pass to Zulfadli.
Okay. Thank you, Dr. Adi. Thank you also to Dr. Lim for the fruitful presentation, and I hope that all the participants could get and then could take the knowledge home. Okay, now before the Q&A session, just like to remind all those who are following our webinar session, please register your attendance for us to keep track and keep record. So now we open for the Q&A session. If you have any questions, please leave your question in the comment section, and we'll try our best to get the presenters to answer your questions. Okay, there's one question from, sorry if I mispronounce your name, Miss Jiap Wachapran. To analyze bone porosity, how to distinguish the porosity from the Hawaiian channel? I open to the presenters for the answer.
Hi. To answer your question, how to differentiate between the bone porosities from the Hawaiian canal, it's mainly based on the structure, because the canal here, the Hawaiian canal, you can see is a tube shape, it's a network, whereas the porosity of cortical layer, the pore size is normally is in irregular shape, even though when you compare the pore, the normal pore of the cortical bone and the Hawaiian canal, and also the osteoblast cells. The osteoblast cells, you can see the shape, the diameter of the shape is with a range of a few micron, like about 5 micron. But for Hawaiian canal, you can see it's a tube shape. You can see all the networking built up and connected to each other. And for cortical bone porosity, you can see the irregular shape of the pores. So from different morphology, you can tell whether they are the original porosity of the bone, or whether it's from the canal, or whether it's from the osteoblast cells. Yeah.
Okay, thank you, Dr. Lim. Hope that answers your question.
Okay, maybe I can add something. Okay, actually we can differential during the reconstruction actually, and with the value shell value. I say in the bone, let's say 1,000 something else, and with the aspiration channel with the different voxel, then actually you can generate different focus with the Hawaiian channel or the porosity of the bone itself, actually.
Okay, so we're still waiting for any other questions. And in the meantime, I would like to share the email address for both presenters. For Dr. Lim, it's ft_lim@hotmail.com.my, ft_lim@hotmail. Oh, sorry, HTI-mail. Sorry. HTImail.com.my. And for Dr. Ardiyansyah, it's rd@utm.my. So if you have any questions that we were unable to answer in this session, I think both presenters are most willingly to give the answers, to give your feedback. So see, there's about 26, 27 participants on our live stream, and still waiting for any other questions. Our session is supposed to end at 12. If there's no questions, I think is it okay for us to end this webinar? Both Dr. Lim and Dr. Adi?
Yeah, sure. Sure.
Okay. So thank you very much to Dr. Lim and also to Dr. Adi for the sharing. Hope we can have more sessions in the future to better educate myself and also to educate the viewers, and also hope we can collaborate more between high tech and also UTM. Thank you for all listeners, and have a good day. For those Muslims who will be celebrating Eid Mubarak, happy Eid Mubarak to you. And for those who are going to be on holiday, then happy holidays. And for Malaysia, it's happy PKP, happy MCO. So stay safe, stay home, and follow SOP. Thank you.
Thank you.
Thank you very much to all.
Yes. Okay.
Okay, thank you.
Bye.
Bye.